Yes. So, I mean, we will quickly go through what I want to discuss for this weekly session number 4, and then we will proceed to your doubts from the last live session, as well as in any question which you are facing related to the assignments. Uh, okay, so this is going to be the fourth weekly live session, and let me just check whether I have recorded, start recording or not. Yeah, it is. Hello everyone, this is going to be the fourth weekly live session of the course of River Engineering. This is a joint scheme of NPTEL and SWAYAM, and this course is being tutored by Professor Subhashish Datta from the Department of Civil Engineering at IIT Guwahati. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme at the Interdisciplinary Center for Water Research at IISc Bangalore. So far we have already uploaded a set of 5 different videos from the past 3 weekly live sessions and the assignment number 0. So in case you get stuck somewhere, or I mean you might have missed out on something discussed during these live sessions, you can again go back to the YouTube videos to check what went wrong. Okay, so that was the first thing, and this is the channel link for that YouTube channel, and the documents related to the live sessions would be immediately uploaded to this Google Drive folder after the class. So today again it malfunctioned, so I just decided to discuss a few questions, and I have straight away pasted the notes which I actually prepared for this lecture, so that I mean we would be able to do two things. First of all, it would be much faster, and secondly, if in case you have any doubts, we can discuss it at the very end, so we can do both the things together. Okay, the first question is basically very much similar to assignment number 5. Yesterday you got your lectures relevant to assignment number 5, so I thought of discussing a few questions in this session from assignment number 5. However, the major parts, major number of questions discussed would be relevant to assignment number 4 itself, because it was not discussed in the previous class. So this is the first question. A 1000-meter gravel bed river reach has a flow depth of 1 meter, a width of 20 meter, and a mean velocity of 0.20 meter per second. What is the prototype Froude number? So after looking at this prototype thing, many people may think that it is a model and prototype problem, which it is definitely not. However, I mean I will just put a light to the this dimensionless entity termed as the Froude number. It represents the ratio of the inertial forces to that of the viscous forces, and we are to apply it only in cases where these two forces dominate. For example, open channel flow, or in case of a spillway. So this question straight away asks you to find out the Froude number. Froude number is the ratio of the velocity of the flow to the square root of the acceleration to gravity, and the d. D happens to be the ratio of the the cross sectional area to the top width. In this case, it is a straightforward. It is a rectangular channel. So the rectangular channel, the cross sectional area will be b times y, that is a width times the depth of the flow, and the top width will be the width. So by b will give us y, so d will straight away will become the y. So we are just putting in the values. It's a very straightforward question. B is given here in the question as 0.20 meter per second. G happens to be the acceleration due to gravity, which is 9.81 meter per second square, and d will be y, that is the depth of the flow, that is 1 meter. We get the final value as 0.0638. Now as someone just asked me that he's unable to get the option, according to what he is getting in his answer. So the thing is that, I mean, even in this question we don't see 0.0638 in any of the option, right? So in that scenario you need to take the option which is nearest to that. So if it's 0.0638, the nearest option would be option D, and that would be the correct option for it. So why this discrepancy is happening is because in some cases someone might have taken the value of G as 10, someone may have taken it as 9.8, Someone may have taken it as 9.79, someone may have taken it as 9.81, and that is why we may get some different solutions related to different approaches of, or different fundamental constants taken. So no need to worry if you are getting different options numerically, but you need to take the one which is closest to your answer. So I think that sorts out your doubt, right, Nagendra?
Yes, sir, that is okay. So other questions maybe in the assignment 5.
Hmm.
So if you are for today or next week 6 to 10, so please give some demo also on those questions as well.
Okay, okay, okay. Actually, I have been advised not to discuss the assignments before the deadline gets over. But I will tell you. I mean, we will look at the questions today, and I will tell you how to solve it. Okay.
Okay, okay, fine.
I've been ordered by the NPTEL authorities not to solve the assignments. Otherwise, it would be unethical. You know, right?
Yeah, yeah,
So
yeah. At least,
we will just discuss it. I will
yeah,
just tell
yeah.
you the concepts.
Okay, fine. That's fine.
So the second question was about a clear water open channel model. Yeah, it is basically a question on models and prototypes. A clear water open channel model is to be designed such that the maximum laboratory discharge is 1.5 liters per second for a stream discharge of 100 meter cube per second. If the laboratory space allows a maximum length of 40 meter to model a river reach of 15 kilometer, determine the scaling ratios of time and discharge. I discussed something very similar during assignment 0 also, which was the prerequisite assignment. I mean, kind of the prerequisite assignment for this course. However, I will again go through the details, so no need to worry about that. So first of all, you need to check that it is an open channel model. An open channel model, it means that the question is indirectly telling you that we have to apply Froude's model for similitude. We are making a model from a prototype. So the two most prominent forces would be the inertial force and the gravity force. Hence the Froude's model similitude needs to be followed anyhow. Okay, so these are the numbers, and they finally want us to report the scaling ratio for the time and discharge. Okay, so I will discuss it. Yeah, so first of all, the length scale ratio, that is how you model the geometric parameters of the, model from the prototype, is basically the ratio between the model and the prototype. It determines how much is the geometric similitude. Okay, so that is taken as LR, and geometric ratio can vary. For example, in most of the cases, the rivers may even have a distorted kind of a model. Why? Because the length scale, the length dimension of the rivers are much larger than their width and the depth or direction. Hence, in some cases, we take different length scale ratio for different dimensions also. However, in this question, that is not told. So, the length scale ratio is taken constant for all the different dimensions, and it is the length scale of the model to that of the prototype. Now we need to find out the kinematic parameters. So that is something which we call as the kinematic similarity. So let us look at the velocity scale ratio. We want to know what the velocity scale ratio will be. So velocity scale ratio is just like the length scale ratio, the velocity of the model to that of the prototype. And velocity of the model is nothing but the length of the model to the time of the model, and velocity of the prototype is the length of the prototype to the time of the prototype. So the velocity scale ratio will be nothing but the ratio of these two quantities, that is Vm by Vp, and Vm and Vp have their own expressions. So you just put it there, and you will finally get this expression Lm by Lp into Tp by Tm, and Lm by Lp is something known as the length scale ratio from the first expression. So it is Lr by Tm by Tp. So Tm by Tp is again Tr, that is a time scale ratio. So that is why we finally get Vr, that is a velocity scale ratio, as the length scale ratio to the time scale ratio, where the time scale ratio is again the time taken by the model to that of the prototype. Similarly, we want to know the acceleration scale ratio. So Am, that is the acceleration of the model, will be the velocity of the model to that of the time of the model. Okay, so the velocity of the model can again be written from the previous expression as Vr times Vp, and the time of the model will be Tr, that is a time scale ratio times the time of the prototype. So it will be written as Vr by Tr times the acceleration of the prototype. So AM will be nothing but AR times AP. So AR is again AM by AP. We could have directly written it, but still we are writing it like this. Now AR, the acceleration is nothing but change in the velocity to that of the time. So we are just considering the dimensions for this dimensional analysis. So it is VR by TR, and VR we know is what VR is LR by TR from the previous expression. So we just substitute LR by TR in this expression to get AR as LR by TR square. The third thing is that since it is a case of an open channel, so we need to ensure that there is a dynamic similarity. Dynamic similarity in easy terms is nothing but we are ensuring the similarity of forces. And by forces, we need to ensure the similarity of two most important forces for open channels, which happen to be the inertial forces and the gravity forces. The inertial force is subscripted by I, shown by subscript I, small I, and the gravity force is shown by the subscript small g. So so Fi, that is the inertial force for the model by the inertial force of the prototype, should be equated to the gravity force of the model to the gravity force of the prototype for an open channel flow. So from this we will get that since the Froude number is nothing but inertial force to the gravity force, so it will become it will actually equate to the equality of the Froude numbers. That is, the Froude number of the model will be equal to the Froude number of the prototype. I have actually derived this expression in assignment number zero's video. So if in order to, in case you want to know how I came from this expression to this expression, you can refer to the YouTube video on assignment number zero. So this is what we want to ensure for open channels or spillways or anything in which the inertial force and the gravity force dominate. So we need to ensure, again I am telling you, we need to ensure that the Froude number of the model is equal to the Froude number of the prototype for dynamic similitude finally. Now let us look at Froude models. How are we actually arriving at them? So first of all, VR square is equal to LR. How did we come at that? I am telling you, since the Froude number of the model is equal to the Froude number of the prototype, so the Froude number length scale ratio will be equal to 1. So from that we get the Froude number scale ratio equal to 1, and we are just writing it in terms of the scale ratios. So Froude number is nothing but V by square root of GL, where L is the characteristic dimension in our case. So we are writing in terms of the scale ratio. So it is basically VR by square root of acceleration due to gravity R times LR, which will be equal to 1 because the length scale ratio of the Froude number is equal to 1. Now GR is equal to 1. The acceleration due to gravity for the model and the prototype are both equal, and that is why GR equal to 1. By the way, this is exactly the first question of assignment number 1. So I mean, assignment number 4. So in case you are getting stuck there, you can. This is exactly that question. Okay. Anyways, so from it we get that VR is equal to square root of LR, and hence we get that VR square is equal to LR. Just squaring the terms, we get that. Now, if the question asks you to find out any parameter in terms of Froude model dynamic similitude, this is the approach you have to follow. So the first thing is that let us suppose there is any physical variable A, which is composed of the dimensional characteristics, length, mass, and the time, and each of them have their own indices, that is a powers. Length power x, let us say the length power is x, the mass power is y, and the time power is z. So uh, I mean, for visualization purpose, let us just suppose the physical variable is force for the time. So the force is basically mlt minus 2. That is how we write its dimensionless. Write it in terms of dimensionless analysis. So for A to be force, it would be mlt minus 2. So y would be 1, L would be x would be 1, and z would be minus 2. So this is the thing. However, we are actually trying to derive the expression for discharge. So I will quickly come to that. So this is the physical variable which can be represented in terms of its dimensional entities. So the So the length scale ratio, so the scale ratio of AR will be represented as the scale ratios of individual dimensional entities. Okay, so let us now firstly come to the mass scale ratio. So mass scale ratio is represented as the density scale ratio times the uh, length scale ratio power 3. Why length scale ratio power 3? Because mass is nothing but density times the volume, and volume is nothing but L power 3 in dimensional language. Okay, and okay, so let us firstly observe what this rho r is. Rho r is basically the density of the model to that of the prototype. And since the model and the prototype in most of the cases are made of the same material, so the densities would also be same, and that is why the rho r, that is the density scale ratio, would be equal to 1. So we get directly mr is equal to lr cube. So this is one expression solved. Now we want to know what is tr. So for tr, I mean, we can directly get, since the velocity was the ratio of the length to the time, we can flip the entities to get tr is equal to lr by vr. We know lr here and we don't know vr, but we now know vr because of the Froude similitude. Since the Froude number scale ratio is 1, so we know that vr would be nothing but lr to the power half. So tr, that is a time scale ratio, would be nothing but square root of lr. So that is also sorted out. Now you just substitute these values in the dimensional dimensional expression. You will get AR is equal to finally LR to the power x plus 3y plus z by 2. Since LR, I mean, since we actually translated all the other dimensional entities into terms of LR, so that is what we will finally get. So if you get any expression in any assignment, any future assignment or any future exam, you just need to go through this first principle thing. You don't need to worry about anything. Just firstly make or translate the entity into its dimensional equations, and then try to get this term somehow, and from that you will get its dimensional similitude expression. So here we the first question asked was about the time scale, which is already found out as square root of length scale, and the other one is the discharge scale. So discharge scale would be nothing but the area scale times the velocity scale, that is ar times vr. Area scale is since area is length into breadth, so it is basically 2 times the length scale ratios, because we are not using a distorted model. So the length scale ratio for the width, I mean, for the width as well as the depth of the flow is same. So LR is same. So it is LR square times VR. VR is represented as LR to power 1 by 2. So QR will be LR to the power 2 plus 1 by 2, which will come out as LR to the power 5 by 2. So this is the final expression for QR. Now the question asks you to find the scaling ratios for time and discharge. Okay, so first of all, we will need to find out the LR, because both the scaling ratio for time and the scaling ratio of discharge are functions of the length scale ratios. So LR is equal to LM by LP, or LP by LM if we are translating it. Okay, so LR is equal to LP by LM. So it is 1 point, sorry. So this, yeah, 15 kilometer by 40 meter is the LR. So you just translate kilometer into meter. So that is 15,000 meter by 40 meter. So it comes out to be 375. Now the time ratio is nothing but square root of LR, which is square root of 375, which is 19.36, which is nearly 20. And discharge ratio is LR to the power 5 by 2, which comes out to be 23191.45. So A would be the correct answer for it. Uh, again, for time scale ratio, we are getting the answer as 19.36, but we are taking the one which is the nearest to the correct option. So A would be the answer. Let's move to the third question. Third is relatively simple and about the Lacey's theory. Yeah, so calculate the critical velocity ratio for the depth of the channel given as 2 meters take the critical velocity ratio as 1.1. Such questions we have also solved a bit in our irrigation engineering classes. However, it is also important for scouring theory. So we are again revising these concepts. Uh, so the critical velocity is nothing but but according to the empirical expression, 0.55 times m times y to the power 0.64. So m here is 1.1, which is the critical velocity ratio. So 0.55 times 1.1 times the depth of the channel to the power 0.64 will finally fetch us the critical velocity, which comes out as 0.943 meter per second. It's a very straightforward question. Something very similar is asked in assignment number 4 also. That's why I thought of discussing this question. The next question is Lacey's scout depth for a stream carrying a discharge of 3 meter cumex per meter width and having a silt factor of 1.2. 1.2. Okay. So we need to know what is the Lacey square scout depth. So it's a straightforward expression as from the video lectures given by Professor Datta. It's q square by f to the power 1 by 3, and small q is nothing but the discharge per unit width. So discharge per unit width is straight away given as 3 cumex per meter width. So just put the values. You put the value of the silt factor, that is small f. You will get the answer as 1.956 meters straight away. Now we move to a question based on the shear velocity. This expression of this shear velocity becomes a very important entity because using it we can find out whether there is going to be an incipient motion of the sediment particles in a river, or whether it is going to be immobile. So the mobility of the sediments is determined by the shear stress and the shear velocity, hence it becomes very important. So this is the question. The question asks us to evaluate the shear velocity for a 100-meter wide rectangular channel having a discharge of 25 meter cube per second and a longitudinal slope of 20 centimeter per kilometer, assuming the f is 0.01. Okay, so it is straightforward given. F is the roughness basically. So normal depth from the expressions of the Manning's equation can be derived like this, which is given in one of the video lectures. This expression is straight away given in one of the video lectures. So it is f q square, small q is the discharge per unit width, uh, by 8g times s naught. S naught is a longitudinal slope, power 1 by 3. Now small q is not straight away given, so it will be the discharge times the width. So it happens to be 25 meter cube per second by 100 meter, and that is how it comes out to be 0.25 meter square per second. Just put all the values in the expression above, and you just don't forget to convert the longitudinal slope into a dimensionless entity. So 20 centimeter by 1 kilometer is the actual longitudinal slope. 1 kilometer would be 1000 meters, and 1000 meter is 100 centimeters. So we just converted both the numerator and denominator into centimeter to make it a dimensionless entity first of all. So you just calculate it, you get 0.34 meters as the normal depth. Now we get something known as hydraulic radius. So hydraulic radius is nothing but the cross-sectional area to the wetted perimeter. One thing to be noted is that it is a wide rectangular channel. So wide rectangular channel means that the width of the channel is much larger than that of the depth of the channel. So one simplification which we could have taken was that in the calculation of the wetted perimeter, that is b plus 2y, we could have taken it nearly equal to the width, but we are not doing it in this expression. We are finding it in exact terms. So the hydraulic radius happens to be the cross-sectional area, which will be the width of the flow times the normal depth by the wetted perimeter, which is b plus 2yn. Okay, just substitute the values to finally get the hydraulic mean radius to be 0.3377 meter. Now we need to find out the shear stress first of all. So shear stress, the formula is gamma r times S naught. You need to remember this equation. This equation comes again and again actually. So don't forget this expression never. Gamma is rho times g. So rho is 1000 kilogram per meter meter cube, and g is 9.81 meter per second square. R, that is the hydraulic radius, came out to be 0.3377 meter. Put that. And S naught is the longitudinal slope. So longitudinal slope is 20 centimeter by kilometer. So 20 centimeter by 1000 meter into 100 centimeter. So we converted 1 kilometer in the denominator into again centimeter. So we get this. So in the next slide, the value of the shear stress is given as 0.66 pascals or newtons per meter square. Now the shear velocity is nothing but square root of shear stress by the density of the fluid. So just finding the number happens to, I mean just solving it, the final shear velocity happens to be 0.025 meter per second. Now we move to the final question of the day. I thought that rather than solving a few easy questions, I will solve a question which basically will introduce the concepts of water flow as well as the sediment dynamics. So this is one such question I found from internet, and this question is very interesting, and it is very similar to the question which I discussed towards the end of the part 2 of weekly session 3 also. So this question will basically clear all your concepts. That's what I hope, and that is why I chose this question finally. So the question states that a sluice is a sluice is placed in an open channel with a horizontal bed covered by gravel with a mean diameter of 5 centimeter and a density of 2650 kilogram per meter cube would be the correction, not kilometer per meter cube. So the density is kilogram per 2650 kilogram per meter cube. The flow rate is 4 meter cube per second per meter width, so that is small q. And initially the depth below the sluice is 0.5 meter. Assuming a critical shields parameter of 0.06 and friction coefficient of 0.01, A, find the depth just upstream of the sluice and show that the bed there is stationary. And B, show that the bed below the sluice will erode and determine the depth of the scout. This is a very interesting question actually, and so it basically firstly asks you, it indirectly asks you to know whether the bed at the upstream of the sluice is going to be stationary or mobile. If it is mobile, means it's eroding. So that is what we want to know. So we have to find it out indirectly using the depth of the water at the upstream of the sluice. And B, it wants us to show that the bed below the sluice will erode and determine the depth of the scour. So we want to know, indirectly we want to know whether the shear stress at below the sluice, is it exceeding the critical shear stress or is it below the shear stress. So the thing is that if the shear stress happens to be lower than the critical shear stress, then the sediment particles will not be moving. It will be an immobile phase. And if the shear stress is greater than that of the critical shear stress, then the sediment particles will be moving and there will be erosion. So that is what this question indirectly wants you to know and wants you to visualize. Okay, so the question is very interesting. First of all, the median diameter was given as 5 centimeter. You just converted it into an SI unit. The density of the sediment is also given as 2650 kilogram per meter cube. So the specific gravity is nothing but the density of the sediment by the density of the water. That comes out to be 2650 by 1000. So it will be 2.65. The discharge per unit width is again given straight away in the question as 4 meter cube per second per meter. Then the critical shear stress is again given as the critical shear stress parameter is given as 0.06. It is not given in magnitude terms, but the parameter is given. Then the friction coefficient in the question is given as 0.01. Okay. So as I told you that the bed will be mobile if and only if the bed shear stress happens to be greater exceeding that of the critical shear stress for incipient motion. Incipient motion means the state at which the motion of the sediment is just about to start. So we want to do two things, ensure two things for this. Number one, we need to find the critical shear stress for the incipient motion. And number second, we want to know whether the local shear stress can be found by finding the velocities using open channel flow theory and using the friction coefficient. So the critical shear stress for incipient motion is found out as by multiplying the critical shear stress parameter, which is a coefficient, with rho s minus rho, that is the density of the sediment minus the density of the water, times g, acceleration due to gravity, times the mean dia of the sediment particles. So this comes out to be 0.06 times 2650 minus 1000 times the acceleration due to gravity is 9.81 meters per second square times 0.05. So the critical shear stress is 48.56 pascals or Newton per meter square. So the thing is that whenever the bed shear stress exceeds 48.56 Newton per meter square, we will see a motion of the sediments, and if it is lower, then the sediments will not be able to move. Now, flow just below the sluice gate was given as zero point 0.5 meter in the question, which was the depth of the flow. So, we are to apply two concepts in the question. Number one, we are to know where, we are to apply the concept related to the specific energy. That is what we will be going next up. So yeah, so firstly we will be knowing the velocity of the flow there. So velocity of the flow happens to be nothing but the discharge per unit width by the depth of the flow. So 4 by 0.5 will give the velocity of the flow to be 8 meter per second. So total head relative to bed will be equal to capital H, which is equal to ZS, that is the depth at the surface, plus v square by 2g. So it will come out to be at the surface of the water, it will come out to be 0.5. Why 0.5? Because the depth of the water was 0.5 as already given in the question, plus v square by 2g. V was found as 8 meter per second by 2 by 9.81. So total head will be 3.672 meter. So the same total head at the upstream of the will exist at the upstream of the sluice too, because of the conservation of the energy. You just need to equate this term. So the total head capital H needs to be equated with the total head at the upstream of the sluice, that is H plus q square by 2g h square. Okay. So small h will be capital H, that is the total head, minus this expression. You just substitute the values of small q, g and 2 into it to get this expression in terms of only small h. So the small h will be finally found at from trial and error 3.703 meters. So the velocity at the upstream of the sluice will be nothing but q by h, just like the expression I showed at the top. So it would be 4 by 3.703, which is 1.080 meter per second. Now, bed shear stress at the upstream of the sluice we need to know. Just to check whether it is exceeding the critical shear stress or not. So, it is nothing but the coefficient of the friction times the kinetic energy here. And kinetic energy in fluid terms happens to be half rho v square. Okay, so it's very straightforward. So just put the values to find out the final bed shear stress to be 5.832 Newton per meter square or Pascal. So we know that the bed shear stress is lower than that of the critical stress, which was 48.56 Pascals. So that is why the bed will be stationary at the upstream of the sluice. So this basically sorts out the part one of the question. So we showed that the bed would be stationary, and the depth at just upstream of the sluice was also found out. Now part B wants us to show that the bed below the sluice will erode and determine the depth of the scout. So we need to know whether the bed shear stress at the downstream of the sluice is exceeding that of the critical shear stress or not. So that is what we want to know. And we also need to know the depth of the scout. Let's find it out. So the velocity of the fluid beneath the sluice is given as 8 meter per second. So let's find out the bed shear stress straight away using the same expression as given in the previous page. So it is the friction coefficient times the half rho v square term. So it will come out to be 320 pascals or 320 Newton per meter square. So tau b, that is the bed shear stress, is exceeding that of the critical shear stress, which was 48.56 pascals. So it is much larger. The critical shear stress was around 50 pascals, and the bed shear stress at the downstream of the sluice happens to be 320 pascals. So it's more than 6 times of that of the bed shear stress. So the erosion would be very rapid. So tau b is greater than that of the tau critical. So the bed is initially mobile. Uh, that is one part of the second question asked in this question, second part of this question. So next we want to find out the depth. So we know that since tau b is greater than tau critical, the bed will continue to erode. So as the bed will erode, the flow depth will also increase. Why? Because the erosion is happening from the bottom of the bed. So flow depth will, water will basically come and take up that space from where the erosion happened. So the flow depth will increase and the velocity will decrease. Okay, so as the velocity is decreasing, we will see that velocity is decreasing. So we will see that the tau b is decreasing. So tau b will decrease only till a level that, I mean, it equates that of the critical shear stress. So at that stage, CF, I mean tau b, we can straight away equate to the critical shear stress. So we get V is equal to this expression. You just take out V from this term, and then tau critical will go down in the tau critical will go down in the denominator, and then take a square root. We will get an expression for uh, V like this. You put the values, you get the velocity as 3.116 meter per second. Now the depth of the flow will be q by v, and where q is the small q is the discharge per unit width. So 4 by 3.116 is, and which happens to be 1.284 meter. So this is the depth of the flow. Now since the downstream water level is set at 0.5 meter above the undisturbed bed, by so the depth of the flow needs to be corrected by 0.5 meter, because it is set at 0.5 meter above the undisturbed level. So 1.284 minus 0.8 will give the final downstream uh, depth of the scour. So it will be 0.784 meters. So that's what I wanted to discuss today. So we discussed six very different kind of questions, out of which questions number one and questions number one and two are very relevant to assignment number five, whereas questions number three, four, five, and six are relevant to assignment number four. In the first question, we learned about Froude's number. It was a very straightforward question. We learned where to apply Froude number and how to find it. In the second question, we did a bit of a dimensional similarity expression for the discharge and the time for the Froude models. We learned that the Froude models are to be used only in cases where the inertial forces and the gravity forces dominate. So that the possible candidates would be the open channel flows or spillways or sluice gates. So those are the cases where the Froude models are to be utilized. So we again derived the expressions for the different scale ratios relevant to the Froude models. Just a caution that, let us suppose this time they're not giving, I mean, even in case they're giving some other physical variable, let us suppose they're giving you some uh, what may be the model, let us suppose they're giving you power. So power is gamma qh. So From that you can find out the dimensional expression for power, and you can come at the same expression using the same funda. So it is kind of similar to the first principle. You just need to understand this thing, and you will straight away arrive at the expression for the fraud model similarity. You don't need to remember any expression, it's very straightforward. You just need to use this thing, and straightforward straight away you will arrive at the final expression after solving it. Yeah, so we did this. Then we found out, we used a bit of Kennedy's theory and Lacey's theory. This was Kennedy's. We found out the critical velocity ratio using this. So in the next question we use the Lacey's cow depth using the Lacey's theory. So these were, I mean, amongst the first few theories, were primarily empirical. Kennedy is definitely empirical uh, to find out the scout depth. Then we came out, I mean, we solved a question relevant to the shear velocity of a wide rectangular channel. We understood how it is found out. The bed shear stress happens to be the gamma r times s. Uh, so we found out tau, and from tau we can find out u star. U star is the shear velocity. U star is actually a very important term, even in boundary layer theory. In case you are going to learn about, in case you are ever going to take a course on advanced fluid mechanics, then in boundary layer theory, this shear stress as well as the U star term comes quite a lot of times. So we found out the U star from the tau naught, that is U star is equal to square root of tau naught by rho. You just remember this expression. This is a very simple expression. You just need to remember one expression for this. And finally, we took a question which would basically aim at clarifying the concepts of water flow as well as sediment erodibility together. So this was a very interesting question in which we understood that upstream and the downstream of the sluices don't happen to behave uniformly. Uh, there may be cases where the upstream of the sluice is eroding, but the downstream of the sluice is not eroding at all, or vice versa. So we need to take different approaches for that. We need to find out, first of all, the critical shear stress. So the critical shear stress is basically uh, a function of only the sediment particles. So the critical shear stress will be constant at the upstream as well as the downstream, and then we need to compare the critical shear stress with that of the bed shear stress at the upstream and the downstream. And how we did it? We arrived at that expression using the velocity, and for velocity we need the depth also. So that depth is to be arrived using the Bernoulli's equation or the specific energy equation. So basically, using that, we somehow arrived at the velocity at the upstream of the sluice. We arrived and got to know that uh, the sluice upstream is not eroding. That is, it's the bed is stationary there, and at the downstream it is eroding. And why it's eroding downstream? The downstream it will erode probably because of the gravity effects being dominating. So that is why there are more chance of the bed to erode downstream of the sluice. So that is what we observed in six questions which were discussed today, out of which four are relevant to assignment number 4, and the first two relevant to assignment number 5. Uh, if you have any question relevant to this or relevant to previous lectures or anything else, please feel free to ask me.
So please refer to question number 8 in assignment 4. So can you please clarify the question? So
Okay, just a second, please. Assignment number 4, question number 8.
yeah.
Okay, the expressions are straight away given in the video lecture. Actually, you just refer to video lecture number 2 or 3 something. The expression is straight away given there. Okay.
Actually, it is shear stress is given, so but there is a symbol tau star, so that I couldn't able to get. So any
I
further?
solved this question actually, and I am getting one of the options. I solved it just in the morning. So
Uh,
in case you still don't get the get any, or did you get any answer which is similar to that? I mean, you may have gotten, let us say, I mean, 0.047. So I mean, is it something like that?
yeah, similarly, and
So
so
in
other.
Nagendra, in such cases, you just take the option which is nearest to that. Why are there discrepancies in the number? Is because someone may have taken a different value of the fundamental constants. Like rather than 9.8, someone may have taken 10 while formulating this question, and that is why the options may be slightly different. You don't need to worry about that. Okay,
Okay,
you just
so
take the
that
nearest option.
okay, so but that your answer is given uploaded as a problem solving session. So I will refer again that
Yeah,
the
the solutions will be uploaded by Mr. Mridu Bhavan Deka. He is the TA from IIT Guwahati.
okay, okay,
Okay, I am basically from IISc Bangalore. I have nothing to do with uploading the solutions. Mr.
oh,
Mridu Bhavan Deka is basically a PhD student and a TA, NPTEL TA from IIT Guwahati itself.
okay,
So that is his duty to upload the solutions, detailed solutions. I
okay,
actually will ask him to upload the solutions today.
no,
Okay,
okay.
no need to worry. Has he uploaded the solutions for the previous assignments, which are
No,
already which I
no,
mean the deadline for which the deadline is over? No.
no, we couldn't able to get any message.
Okay, I will give him a reminder then. Okay.
Yeah, yeah.
Okay. No, I mean,
Okay,
since we belong to different institutes, so my responsibility is to take a live weekly session per week. I am basically
okay,
a PMRF student, so that is my responsibility from NPTEL.
okay,
Uh,
okay.
Mr. Deka comes directly under the touch of Professor Datta. So
Ah,
he actually handles the solutions and everything.
ah,
Okay, Nagendra. So
okay,
that is
okay,
his duty basically. I will give him a reminder today.
okay, okay.
Anything else? Anything else you are not able to solve?
Yeah, that one only. So question number, I think 9 also similar lines, right? So that is a straight away question.
Yeah, yeah, yeah. It's
That's
gamma
fine.
QH. I mean, you just
Yeah,
use the equation here.
yeah. I couldn't able to exact one, but nearer to the one I am getting. Okay, okay then. Thank you.
This question is, by the way, is the most challenging one.
Yeah,
Question
yeah,
number 10 is the most challenging one. So please do it very. I mean, you have to use all the concepts of salinity for this.
yeah. Straight away you can get. I think.
So this this may cause a few headaches actually. And in assignment number 5, I was also checking assignment number 5 in the morning. This I already actually discussed
Yeah,
indirectly.
yeah. That's fine.
All the other questions happen to be theoretical. This I discussed in my first weekly live session also. So this
Okay.
should not be difficult. Uh, Prototype shield parameter again. Shield parameter straight away equations are given. Okay, some
Yeah,
equations you need to memorize. Unfortunately,
yeah,
although
yeah,
I don't like that thing, but you need to memorize a few equations. If you memorize them, then this course is very simple.
yeah.
Okay, and in my weekly live sessions, I tried that the least number of equations are to be used. I mean,
Mhm.
even if I mean, deriving something, I want you guys to understand that how it is being derived, and it should not be a pain, basically. I mean, that is what I intend to do. However, since I mean, as this course is now transgressing into the sediment dynamics from water flow, the earlier sessions were about water flow primarily. Now it is primarily about dynamics, and sediment dynamics is mostly an empirical field. So there are a hell lot of equations in it.
Mhm.
That's a problem. That's a trouble. I mean, frankly speaking. So
Yes.
you will get more number of equations as you move into the later part of this course. You just need to remember a few of them, and then it will be relatively easier. Okay, and this question I also solved. It's very easy again. Okay. This I also solved. You will be able to solve, I hope, most of them. Did you try assignment 5 also? No.
Yeah, right.
Because
So that
assignment number
eight,
5 was given, I think, only yesterday. We may not
yes,
have
yes,
got a lot of time in solving it.
yeah.
Did you
Maybe
get
eight
a
and
chance?
yeah, 8 and 10. If you can able to just maybe some idea, or maybe next week if you can able to similar problem, or maybe eight
Okay,
and
okay.
ten.
I will just give a hint. There is a straightaway expression for the abutment scout depth. You need
Yeah,
to use that expression for this.
yeah, yeah.
Unfortunately, I mean, as we are transgressing into the sediment part of this course, there are straightaway equations, and those equations are not cannot be derived because they are empirical.
Yeah.
That is a trouble. There is an expression for apartments scout depth straightaway. So eight will be solved using that. Ninth is straightforward.
Yeah.
10th again depth of scout, so you need to use that expression again. So I have solved 10th. You need to use the just go through the video lectures, and
No.
I would just advise you to make a list of the formulae and then check which formula can be applied there. You will get the answer there. Okay, finally.
Yeah.
And this is about the prototype. So this is prototype. This is not a model and prototype thing. Then this is, yeah, this question indirectly was solved by me. This is a very simple question, by the way.
Yeah. Yeah.
Then this, the scale ratio for the acceleration uh,
Yeah.
would be a particular number. Why?
Yeah.
That
Yeah.
I also explained in one of the live sessions. Yeah. So this assignment number 5 is relatively easier than assignment number 4, and assignment number 4, the last question is something which you need to understand very well, because
Concept based question.
yeah, yeah, this is the most concept based question here. Otherwise, all the other questions are basically formula based. Yeah. Did you also understand the last question which was discussed in the previous live session,
Yeah, that one actually for
which
every.
unfortunately I could not show you
Yeah.
because of the malfunctioning? It was from part 2. Did you understand that?
Yeah, we could get through. Main concern is about for a trapezoidal channel, the critical depth expression. That
Yeah, yeah.
already we given q square t by g a cube equal to 1.
Yeah,
So
yeah,
we
yeah, yeah.
we
Rather
applied that
than, I
one.
mean, rather than memorizing, you should
Yeah,
use that equation. I mean
yeah,
that
yeah.
whatever that is. Okay, so
Yes.
using that, you will finally get all the expressions. I mean, even if you
Yeah,
forget it in between the exam, you will derive all the expressions within 1 minute. It won't take a lot of time. And the second question, I was more curious about the second question of part 2. Did you understand that?
which one? The
The
question?
one in which the specific force was derived, basically. I mean,
Specific force. Yeah, that one you have given, right? Yes.
that is again a very conceptual question. I think that is so far the most challenging question. The next challenging question would be the last question of this assignment number 4. You
Okay.
just try it. You just try it. I hope you will be understanding it. You will
Yes.
you will get an answer. Okay, so no need to worry about it. Just try it. This question is actually going to distinguish between people who have understood the concepts and people who have not. So apart from that, all the questions are very simple
Yeah.
in assignment 4. So just, I mean, I will just request you to check the second question of part 2 of the previous weekly live session. That is
Yeah.
also very conceptual. So from that you will get something. I mean, you will understand something.
Yeah.
Anything else you want to ask? Anything else about this course or anything apart from that?
Yeah, that one only if you, maybe at the end of all sessions, if we could able to summarize formulas or concepts, some like a document, so that could be more helpful. So to refer, so before attending for the final exam, and so that may be great help from you if you could able to provide.
Okay, definitely, definitely.
Yeah, yeah,
I am going to take 8 weekly live
yeah.
sessions.
8 week
So
live sessions from that one.
So in the last session, before summing up the class, I will make sure to summarize basically. So
Some
no need to worry about
summarize
that.
and that document if we can able to share to us, so we can able to refer for the exam
Yeah,
point.
I'm sharing everything, right? I mean, by now
Yeah,
I will share
yeah,
everything with you. No need
yeah,
to
yeah,
worry.
yeah, yeah.
So today again this malfunction. So I think from next class onward, actually I repaired it, but it again malfunctioned. So from next class onward, I will be typing the equations, and we get another benefit because of that. That we can now basically discuss more questions. I mean,
Yes.
if we are just going to discuss, I mean, slides like this, then we can discuss more questions. So that is one benefit related to that.
And maybe one request from us, so maybe in the next session, so assignment for 8 and 10 questions, similar one or concept, we can able to give some idea, so that could be more helpful also.
Question
Okay.
number 8 of assignment 4.
Yeah, assignment 5, 8 and 10. Assignment 5, 8 and 10, similar, the concept at least, so our formula. So because
8
we could
and
not,
10, right?
8 and 10, we could not able to get, exactly find out from the
You
lecture
will get
also.
it. You will get it. I mean, 8 for 8. I'm giving the hint.
Yeah.
There is an expression for abutment tau depth. So
Yeah.
you will get it through that.
Yeah,
And
those,
10th, I will give it in the next
yeah,
class.
those
I
two
mean,
only.
the deadline is
31st
31.
one. Mm.
The deadline is 31, but the next class will be before that. Actually,
Yeah, 20.
I mean, NPTEL has asked me not to discuss the question straight away. I mean, so
Yeah, at least some idea or
okay, idea
formal.
will give. No
Yeah,
need to worry about that.
yeah,
Okay,
yeah,
no need to worry. I mean, this lecture was actually primarily for assignment number 4. So I mean,
yeah,
that is
yeah,
why. I mean, okay, I will in the next class I will do that.
yeah.
Anything else? Anything else from the lecture or the previous sessions or anything?
That's fine.
That's it.
Yeah, yeah.
Okay, then I will stop recording.